familiarize everyone what this course will be offering to the learners. Then we'll see how the course is divided into 12 weeks of content starting from week 1. We'll first have a basic overview of concrete as a construction material. We'll talk about components of concrete and concrete as a composite. Then we'll see the main part of discussion where we'll go into cement as a binding element of concrete, its production, composition, microstructure, hydration, kinetics, and presence of water and pores in the cement paste assembly. The theoretical part that we will be discussing today would be just a quick recap to the week's content, where if anyone has any doubts they can ask any of their queries. Along with the theory, in between I will introduce you with several questions to challenge your understanding of the subject. So in today's session, in total there will be 12 such questions that we will discuss, and at the end I will make myself available to solve your queries related to assignment questions also. So I hope everyone are clear with the flow of the session. I will just advise everyone to attend the sessions regularly, as it will help you to have a thorough understanding of the course. And whenever anyone has any doubt, they can just type in the chat box or unmute and speak. In between, I will stop my presentation and have a look in the chat box also. Okay, so let's start. So
Okay, sir.
So this course will help the learners to equip with the first-hand knowledge of concrete properties and concrete applications. Okay, by enabling a detailed discussion regarding the ingredients and concrete utilization in modern construction. Okay, so in this course, we'll cover five basic elements of concrete technology. First is the material and selection, materials and properties, where we'll talk about basic materials used in concrete like cement, aggregate, water, admixture, and we'll explain what are the roles of each material and what are their properties. Then second part will be mix design and proportioning, where we'll see the principles of concrete mix design, focusing on achieving a desired strength and durability through proper material proportioning. Then we'll talk about production and quality control, where we'll discuss about processes of mixing, placing, and curing concrete, which helps us to have a proper quality control of our manufactured concrete. We will see various special types of concreting like high performance concrete, self compacting concrete, and fiber reinforced concrete. And finally, we'll talk about durability and sustainability, where we'll talk about durability issues in concrete like corrosion, and we'll introduce ourselves to sustainable practices in concrete production. So it's a 12-week course starting from week 1, where we'll have a discussion about an overview to concrete and cement, mainly in terms of production and composition. And we will end at week 12, where we'll discuss about special concrete and sustainability in concrete production. So basically, this course is divided into 12 weeks of content. Today is week 1 discussion of basics of concrete and cement. Then we'll move to week 2, where we will talk about properties and testing methods of cement. Then we'll move to week 3, where we'll introduce ourselves to aggregates and chemical admixture. Then week 4 will be about mineral admixture. Week 5 and week 6 will be about mixture design of concrete. Week 7 will be about production and quality control. Week 8 will be about mechanical properties. Week 9 and week 10 will be about durability of concrete. Week 11 and week 12 will be about special concrete and sustainability. Okay, so let's start with the week 1. So we are all well versed with the fact that in the present world, concrete is the most widely used construction material, and the facts supports this statement, as it is the second most consumed material on earth after water, and more than 5 billion tons of concrete is consumed every year. But what makes concrete so special? Why concrete? It is because of five key characteristics of concrete. First is behavior, second is strength, third is affordability, fifth is durability, and fifth is flexibility. So behavior, concrete can act as a barrier, which like excellent water resistance property. Strength, it can withstand load. Affordability, it has easily available raw material and it is cheaper compared to some other construction material like steel. Durability, a concrete structure has a significantly high lifespan. And flexibility, we can mold concrete into any desired shape and size. Okay, now how we define a concrete? So, concrete is basically a kind of an artificial stone like mass, which is a composite material created by mixing binding material like cement or lime along with aggregate, water, admixture in a specific proportion. So, in a layman, if we try to write it as a formula, we can say that concrete is equal to binding material plus water plus fine and coarse aggregate plus admixture, which is an optional proportion. So, in a layman term, if I try to define concrete, so concrete is a material which is a flowable slurry kind of thing in this initial start, but with time it hardens and sets into a definite mass which can resist any load or action. Now, if we see different components of concrete, each of the component has a very specific role in concreting, and that's why we need to study each component separately to understand the composite action of concrete. Okay, so first is the binding material. Binding material is the main element of concrete mixture, and cement is the most commonly used binding material, as we know. Okay, now this binding material combines with water, which is provides workability to concrete initially, and it produces a paste which hardens and gives concrete a stone-like characteristics. We have fine and coarse aggregate, which are inert material, where sand is used as a fine mixture, and crushed stone aggregate is used as a coarse mixture, and they provide dimensional stability. And we have admixture, which can be chemical or mineral admixture, which are added as an additional part if we want to enhance the performance or durability of concrete. So all these when they combine, they make a stone-like mass, which is known as concrete. Okay, so today we'll start with the binding material part, and slowly, as the course will progress, we'll cover all the things. Now, based on the proportioning of various ingredients that are used in concrete and admixture content, concrete can be classified into different types. So, here I have listed just a few types, but as per now, there are at least 23 different types of concrete that are listed. Okay, so we can see how the variation in proportionality and how the variation in ingredient can give us such a wide variety of concrete material. And among the listed categories, the most commonly used concrete is the reinforced concrete. So, as we will progress in this course, we'll understand that concrete is a brittle material. It has high compressive strength but very low tensile strength. Now, in actual application, there is both tensile strength and bending compressive strength that is required from concrete. So, where the tensile strength will come from? It will come from the steel reinforcement, which will take up the tensile load, and the composite of a concrete and steel gives us the reinforced concrete, like you can see here, which is used in major infrastructure applications. Okay, now the first part of concrete composite is the binding material. So among various components of basically binding materials are classified into two types, OPC and lime. Okay, so lime is has been used as a building material for thousands of years, dating back to ancient times where Egyptians, Greeks, and Romans started using the lime for concreting. In India, in historic time, lime was a key ingredient in making surkhi, which was mixed with surkhi and stones to make mortar, which was used for making artificial structures like forts, temples, and palaces, uh, which are still valued for their strength and durability. Okay, so if we simply understand how lime was used as a binding material, we can see through this lime cycle. Okay, so lime as a binding material is produced by heating limestone at a higher degree temperature of 700 and 800 degrees Celsius. Okay, when limestone is heated, it converts into quick lime, which when mixed with water become make slake lime, and this slake lime upon carbonation hardens back into limestone. So this cycle makes lime a durable, reusable, and eco-friendly construction material. Now, based on the source and the reactivity of lime, there are two categories of lime. One is hydraulic lime and one is non-hydraulic lime. So, can anyone tell me what is the difference between these two, hydraulic lime and non-hydraulic lime? Does anyone know?
Hydraulic lime requires water to set, whereas non-hydraulic lime requires carbon dioxide to set.
Why is that so? Like, why hydraulic lime requires only water to set?
It's the ingredients and the properties which are there in the lime,
Hmm.
gypsum, plaster, and oxychlorides, which are there in non-hydraulic lime.
So, like, what are the special ingredients that are there in hydraulic lime that makes it different from non-hydraulic lime? Can you tell me the key ingredients? So this is like I will give you some time to think about this, like couple of minutes. So please think about these three questions. What is the difference between hydraulic and non-hydraulic lime? Which one of the following properties is the weakness of lime as binding material? And one modern application of lime as construction material. Whosoever knows the answer, just write in the chat box so that everyone gets a chance to think about the answer. And if you have any queries in the discussion till now, you can regularly post in the chat box. I will see, I will try to answer back. Okay, hydraulic lime has amorphous and non-hydraulic lime is crystalline. Hydraulic lime is limestone plus Ka plus silica plus alumina. Q2 answer A. Uh, for question two, answer won't be A. We'll discuss why. Okay, so let's see the answers now for these three questions. Okay, so non-hydraulic lime, as someone said earlier, it was correct. It sets only by reacting with CO2 in air and forms CaCO3. Okay, so this is for non-hydraulic lime. While hydraulic lime, it sets in water and it does not require air. Like it is not mandatory that air is needed for its hydration, for its setting, we can say. Now, what is the thing that is making the change between non-hydraulic lime and hydraulic lime is the presence of impurities. So in hydraulic lime, there are impurities of silica and alumina, which makes lime reactive towards water and it can sit via cement hydration even without exposure to air. So later on, we will see how in modern world this concept of hydraulic lime was used to make pozzolanic materials. So later on, somewhere in week 2 discussion, we'll see how this concept grew and made what is nowadays known as pozzolanic materials. Okay, so this is the difference between non-hydraulic lime and hydraulic lime, and this is the reason. So hydraulic non-hydraulic lime is pure form of it is pure CaCO3 which sets only in air, while hydraulic lime has impurities of silica and alumina which gives it the ability to set in water also without requiring air for the setting. Okay. For the second question, which of the following properties is weakness of lime as a building material? So weakness of lime as a building material is its strength. Okay, it has a lower compressive strength compared to modern building materials like cement, which makes it less suitable for heavy load applications. Okay, so for second answer is strength. Third, mention any one modern application of lime as a construction material. Did anyone answer for that?
It can be used for thermal insulation and
Okay, but for thermal insulation, we also have very modified types of cement which are generally used. If I can say very simple application of lime as a construction material nowadays is in the repair and restoration of old heritage structure. So it is repair and restoration of heritage structures. Why? Because heritage structures were originally composed of lime, and so if we are using lime as a repairing material, it will be compatible with the with the material used in the heritage structure, and which will make it as ideal material for preserving ancient building. Okay, so mostly lime nowadays is used in this activity. Okay, this is the most common application. There can be other applications also, but I just listed one of the most common application. Okay, so this was about lime, how lime was used as a binding material, what are the different types of limes, what are the different types of lime, and what is one common application of lime nowadays. Okay, after lime we have cement as a binding material. So first let's explore the history of Portland cement, how it came. So when we talk about history of Portland cement, there are three important facts that we need to know. So it was in the early 19th century when one scientist, we can say Louis Joseph Vickers, he first prepared Portland cement by calcination of a mixture of limestone and clay. Okay, so by calcination of a mixture of these two things, he first prepared the Portland cement, which laid the formation for the development of Portland cement. However, it was in 1824 when a scientist named Joseph Aspidine he patented the hydraulic cement and gave it the name Portland cement. Okay, and how this name came? So this name Portland came because the cement that this person made, it resembled the property of a Portland stone which was found in a region called Dorset in UK. Okay, so because of its familiarity with the stones found in this area, the cement was named as the hydraulic cement that was produced was named as Portland cement. Okay, so we can see in the map also Dorset is here in UK, and in Dorset there is a location known as Portland, from which the cement name came. Okay, now how the cement is produced, how Portland cement is produced. So it has five key stages. So stage one is crushing of raw materials. Okay, so it all begins with the crushing of raw materials that are limestone and clay into smaller particles. Once we have crushed the raw materials, we will go to stage 2, that is grinding, proportioning, and blending. Okay, so the crushed materials are now grounded and blended into precise proportion to create a homogeneous mixture. Okay, Now, after grinding and proportioning it, we come to stage 3, which is preheating of raw materials. So this mixture that we have formed, it is preheated with using the hot gases which are released from the kiln, which helps to reduce the energy consumption later on. The fourth and the main stage of cement production is the kiln phase. The pre Now this material which is preheated, it goes into the furnace. Okay, where it is heated to very high temperature in a rotatory kiln, where all the cement reaction takes place, which forms clinkers. Okay, so there are basically four stages of four different zones of temperature where the reaction and the blending of cement happens. So first is up till 100 degrees Celsius, all the evaporation of water happens. From 100 degree to 430 degrees Celsius, dehydration and formation of oxides of silica, alumina, and iron takes place. In the range of 900 to 1000 degrees Celsius, CO2 is evolved and CuCu is produced through calcination. So limestone, it converts into free lime and plus CO2 in this temperature. Now we have silica, alumina also there, we have lime also there. So at 15 and up near 1500 degree temperature, the cement clinkers are formed after reaction of CO with the silica, alumina, and iron bearing phases. Okay, so these are different temperature ranges where all the clinker formation takes place. So clinker is basically the final product from which we get after the reaction of raw meals, limestone and clay. Okay, and with some iron impurities also. Okay, now where after passing to rotating kiln, the clinkers are stored in a silo, uh, where they are allowed to cool. And once the clinker are cooled, gypsum is added to the cement, and the mixture is powdered to make cement. Okay, so clinker is mixed with gypsum and then it is powdered to make cement. Okay, that powdery cement is what we use. Okay, so this is stage 5, cooling and final grinding of clinker with gypsum. So you'll see later on why we are adding gypsum when we'll talk about hydration of cement. Okay, now since we know both cement and lime, okay, we have seen how cement is produced, and earlier we talked about how lime is produced. So I will ask two questions here. Can anyone tell me what is the difference between hydraulic lime and cement? In hydraulic lime, also you saw impurities. In cement, you saw it is also composed of limestone and clay. Okay. And second question is, what are the sources of CO2 emission in this clinker production? So if everyone has understood this process of how the clinker is produced, can anyone tell me what are the sources of CO2 emission from this clinker production? Try to answer these two questions. Decarbonation of CaCO3 at high temperature. Yes, that is one point. Okay, so let's see the answer for these two questions. Okay, so we have two things here. One is hydraulic lime, I am representing it by HL, and one is cement, which I am representing by C. So, hydraulic lime, it sets by water and CO2 both, it can use for setting. However, cement only sets by water. Okay, that is one difference. Second is the temperature range at which they are produced. So hydraulic lime is produced when limestone with impurities of clay and other minerals, it is heated at 700 to 800 degrees Celsius, while cement is produced by heating the impurities of limestone, clay, silica, iron till 1500 degrees Celsius. Now, why this temperature range is important? So, basically, you will see later on, this is the reason why lime has low strength compared to cement. It is because of the heating temperature. At lower heating temperature, there are certain phases that are not formed in lime, which is formed in cement, which makes lime a weaker material compared to cement. Okay. One thing which is advantageous in case of lime, hydraulic lime, is that it is more breathable, and that's why it is used for restoration, while cement is more compact and a dense material, which makes it more durable and resistant in harsh environment. Okay, so the strength part we'll see later on when we'll talk about these phases C3S, C2S, and all, and how they differ in lime and cement. Then when we'll understand this, you will get the answer of this question. Okay. For the second question, the answer is both decomposition of limestone. So CaCO3, when it decomposes, it produces CaO plus CO2. So here is CO2 emission, and burning of fuel also produces liberates CO2 gas. So both B and D will be the correct answer. Okay, so now after passing through the kiln phase, both limestone and clay, upon exposure to very high temperature, form oxides of calcium, silica, and aluminium, as we saw here in this discussion. So here we saw in above 900 degrees Celsius till 1500 degrees Celsius, there is dehydration, and from in this three temperature range, we saw how oxides are formed for due to burning of limestone and clay. Okay, so we have calcium oxide, silica oxide, alumina oxide, iron oxides, where they are formed due to heating of limestone and clay in the kiln phase. Okay, so for a Portland cement, to produce Portland cement, the composition of oxides that are required are in the range as shown below. So generally, CO is in this range, SiO2 is present in this range, Al2O3 is present in this range, Fe2O3 is present in this range, and we have minor proportions of other oxides also, of like magnesium oxide, alkalis, and sulfates. Okay, sulfur oxide. Okay, now this thing, the proportioning of oxides in the Portland cement, the composition of oxides in the Portland cement was first demonstrated in 1887 by a scientist named Leigh Chateliers, where he demonstrated that clinker contains several different minerals. And in 1897, it was discovered that these minerals, when they combined together, they form compounds which are known as halide, halide, silicate, and ferrite. These specific names were given to those compounds. Okay. So from these formed oxides that we see earlier, they blend to form solid solutions of different calcium compounds at very high temperature ranges, and these chemical compounds are named in the table as this tricalcium silicates, which is formed, dicalcium silicates is formed, tricalcium aluminate is formed, tetracalcium alumina ferrite is formed, and we have gypsum. Okay, so dicalcium silicate is tricalcium silicate is commonly abbreviated as C3S, is known as halide. We have C2S, which is known as belite. We have C3A, which is commonly known as named as aluminate, and we have C4AF, which is termed as ferrite. Okay, and based on the oxide composition of these species that we had earlier of calcium, silica, and alumina, the specific proportions that are found in the Portland cement of the chemical compounds are in this range. Okay, so in this figure, we can see how the raw material and temperature varies with time. So initially we have limestone, clay, and silica. Okay, silica quartz is like pure form of silica, we can say. And we have iron oxide in small proportion, which up till 600 degrees Celsius mainly loses moisture or may show some phase conversion, like from beta quartz to alpha quartz. Okay, beyond 600 degree temperature, the limestone starts decomposing into calcium oxide, liberating CO2, and subsequently we see belite and certain calcium aluminate phases starts forming. So belite is C2S. Okay, so we have lime, free lime, and we have silica, which is produced from quartz. They starts combining to form belite, and beyond 1200 degrees Celsius, belite starts converting into halide, which is C3S phase. And while calcium aluminate phases start to appear as a solid solution. Okay, this we can also relate to the difference between the hydraulic lime and Portland cement that we just discussed. So in hydraulic lime, limestone is heated till temperature of 700 to 800 degrees Celsius. That's why it is composed mainly of belite. Okay, while in the production of Portland cement, it is heated up to very high temperature where belite start converting into halite. And that's why there is a difference in the chemical composition of both limestone and Portland cement. And this makes Portland cement show higher strength orders compared to hydraulic cement. Now, there is one important factor that becomes like a primary quality assessment of a clinker just after production, and that factor is known as lime saturation factor. Okay, so this factor governs the ratio between the halide and the belite phase, and it shows whether the clinker that we have formed finally is likely to contain any unacceptable level of proportions of free lime. Okay, so we will see later on in week 2 why free lime is a problem. So it is undesirable to have free lime in cement because it causes some cracking problem in concrete. So that's why post clinker production we check whether how much free lime is there in our clinker, just to ensure that it is of good quality. So this is the formula that we use to calculate lime saturation factor. So it is the ratio between free lime CO upon SiO2 plus Al2O3 plus Fe2O3 with certain multiplication factors, and these factors give us how much free lime would be there in the final clinker. Okay, so there is a certain set of reaction which governs the conversion of oxide to compound, and based on that certain set of reaction, we can estimate if there will be a higher proportion of lime there in our final product. Can you please mute yourself? Okay, so this is just a first check of clinker. Okay. Now, before passing a material through the kiln phase, if we know the oxide composition of our raw meal, we can determine, or we can even just adjust the proportion of a raw meal to get a certain compound composition in the final clinker. So initially we know we have limestone, we have clay, we have iron oxide source, we have all the things. Now, if we know the oxide composition of our raw material, we if we can estimate what is the final compound composition that will be formed, we can control our production process. And this estimation of final compound composition from the oxide composition is done using what is known as Bogue's equation. Okay, so this Bogue equation, it relates the oxide composition to the compound composition. So here you can see what how much percentage of C3S will be formed. It can be determined if we know the oxide composition of our raw material. C2S proportions we also can also get from the raw material. C3S, how much it can form, we can also get from the raw material. C4AF we can also know. So these are the four key compounds that we need to know in our final cement, which will help us to identify the properties of cement. We'll see later on how these four phases govern the property of the cement. But using Bogue's equation, we can easily relate based on the oxide composition what will be the compound composition, and will there will be like some excess lime which is left, which can cause uh, uh, undesirable load to our cement. Okay, so let's see one numerical here so that everyone gets familiarized how to use this both of these relations that we have just talked, and how to calculate compound composition and lime saturation factor. So this is the question. Determine the compound composition from the given oxide composition, and also check for the lime saturation factor. So I've given you a oxide composition for a ordinary Portland cement. We have CaO, we have SiO2, we have Al2O3, we have Fe2O3, we have MgO, and we have SO3. Okay, I am assuming that other compounds like alkali oxides are ignored right now. We have just these five major proportions in our cement. So just do the calculation and see what values are you getting. Any doubts till now? Just let me check once. Okay, no doubt. I will wait for like a minute to let anyone do the calculation and tell me the values. Has anyone got the answer? So, Rahul, basically, for using Bogue's equation, we should know the amount of oxides before doing the calculation. If we know the oxide composition of our clinker, then only we can estimate the compound composition. And there are different microstructure testings available in by which we can estimate the oxide composition of a material. So suppose you have taken small amount of limestone clay, you have grinded it properly, and you have made a initial raw meal that we feed to clinker for in the kiln. So that uh, is everyone encountering a voice issue from my end, or it is just specific to few people? Can anyone tell me? Am I audible?
Yes,
Yes,
sir.
sir.
Okay, that must be due to some network fluctuation. But don't worry, these sessions will be are recorded and they will be uploaded and shared with you. So if in betweens you are not able to understand, you will have the lectures recording with you, in which you can listen back. Okay. So as I was answering, there are different methods by which you can estimate oxide composition. There, and if you know the oxide composition using Bogue's equation, we can calculate the compound composition. Okay, so I will just answer quickly so that we can move ahead. So C3's content, upon calculation, you will find it will be 46.5%. C2S content will come out to be 25.39%. C3A will come out to be 10.183%, and C4AF will come out to be 9.21%. And if you have calculated lime saturation factor, it would have come out to be 0.927. So if you haven't done the calculation, just try to use the equation and do the calculation and check if you are getting the same results or not. Okay, so let's move ahead. Okay, so now we know the composition of our formed Portland cement. But now we have three big questions in front of us. These questions are: why cement is reactive, why certain compounds are formed, like we saw C3 is forming, C3S is forming, C2S is forming, why only these phases are forming, and third, how cement reacts with water. Okay, so to answer and understand them, we need to understand the microstructure of cement first. Okay, so basically, we'll first answer why certain compounds are formed. Okay, so basically, cement has mainly two phases. We have silicates and we have aluminates, which reacts with lime to form certain compounds. Okay, so let's first talk about silicate structure. Okay, so silicates are basically represented as silicon oxygen tetrahedra, SiO4 to the power 4 minus, and this is the fundamental building block of all silicate mineral. Okay, now each tetrahedra here consists of one silicon atom which is covalently bonded to four oxygen atoms, like you can see in this figure. Okay, so in a silicate mineral, in a silicate grain, we have one silica atom which is covalently bonded to four oxygen atoms. Okay, now the presence of this leftover unbalanced charge that is there in silica, in silicate, uh, leads to the ability of silicate to show linkage and polymerization through the oxygen atom. Like you can see here in this figure. Okay, so due to the presence of one unbalanced negative charge, silicate has a tendency to link and polymerize with other silicate grains and form a and do show polymerization. Okay, so if the tetrahedra upon linkage and polymerization, if they are arranged in a very 3D periodic pattern, then it is known as a crystalline material. So a crystalline material is something which has a ordered arrangement. So if the silicate tetrahedra they are arranged in the periodic pattern in three-dimensional space, it will form a crystalline material like quartz. Okay. However, if the silicate structure is not highly polymerized, or it is, we can say it is relatively isolated and not only moderately linked, it will retain certain negative charges which will make it reactive and amorphous, and that's why cement is amorphous reactive because of this property, because of the presence of amorphous silicates. Okay. Now, in cement, silicate ion's negative charge is balanced by calcium ion to form two stable compounds. So we have silica oxygen tetrahedra, which has four negative charges which are unbalanced, and we have calcium ions which are there to balance these charges. And calcium ion balance these charges by forming two stable compounds. One is known as halide, and the other one is known as belite. Okay, so in halide there is moles of calcium ions which combines with the silicate and 1 mole of oxygen to form a C3S phase. Okay, so in this oxygen is bonded to six calcium ions, and calcium ions are balancing the charge, unbalanced charge on the silicate. Okay, so if I can just zoom in this photo so that everyone can see. Okay, so here you can see how the structure of calcium C3S looks like. So here we have orthosilicate silicate ions. These are calcium ions, and these calcium ions are balancing the unbalanced charges on the silicate ions. So per silicate ion, there are two calcium ions that are bonded, and in between we have uh, atoms also, oxygen atoms also, which are balancing the leftover unbalanced charges. And this is how it is arranged. So it is like a AB arrangement. Okay. And we have belite phase. Second is the belite phase, where two calcium ions combine with the silicate ion to show structure like this. Okay. So here we have a silicate ion, orthosilicate ion in the middle, and we have calcium ions all around, which is balancing the unbalanced charges. Okay. Uh, in this image also we can see, so this yellow part, it represents C3s. Okay, it has a higher, larger size, whereas this blue part represents the C2s, which has smaller size. Okay. Now, after silicates, we have aluminate structure. So aluminates have aluminium oxygen tetrahedra. Like silicates, it is also has a tetragonal structure, and it is represented by AlO4 to the power 5 minus. So like silicates, these aluminates also have tetrahedral units. In this case, aluminium ion is at the center of the tetrahedron, and it is surrounded by four oxygen atoms. Okay, now the unbalanced charges that are there in this aluminum tetrahedron, it is balanced by the calcium ions by forming C3A, where three calcium ions are balances one aluminate tetrahedron. Okay, so just how we discussed in the silicates, where the unbalanced charges on the silicates are balanced by the calcium ions. In the aluminate also the same thing happens. The unbalanced charges on the aluminate tetrahedra, it is balanced by the calcium ions. Okay, while calcium ion balances the unbalanced charges on the aluminate tetrahedra, it builds a ring-like structure where we have six AlO4 tetrahedra, which forms this composition, like you can see here. Okay, so this is the structure that calcium, upon interaction with the alumina, it forms. However, unlike silicate, aluminate doesn't show any kind of polymerization. So in silicates, we saw that silicates can do show polymerization. They can show linking with other silicate tetrahedra, but in aluminates that doesn't happen, and it has a very simple cubic structure, like you can see here. Okay, so you can see here, this is a simple cubic structure where we have aluminate as a ring and a calcium ion in between. And this is the reason why C3 is more reactive than C2s and C3s, because of its very simple open cubic structure, and the reason that it doesn't show any kind of polymorphism. Okay, so this is the reason which makes C3 more reactive than C2s and C3s. Similarly, we have ferrites also, so has two kinds of structure. Uh, we have tetrahedral structure and we have octahedral structure. However, ferrites are not major compounds that we need focus, so that's why I will skip this part of discussion. Now we know why certain phases in a clinker production is formed, because of the stability of the final product. However, why these phases are reactive? Why C3s, C2s, and C3A? Why they are reactive? Okay, so if you see, there is one common feature in all the cement minerals. That is, it has a very large anion which is bonded to very small sized calcium cation. Okay. Due to the large anion size, if we just imagine a simple cubic structure, so suppose this is a simple cubic structure, we have a cation in the middle and we have very large anion all around. Okay, so due to the large anion size, there is there is a hindrance in the packing of this cubic structure, and since it is known as that packing efficiency of the compound should be in the range of 0.64 to 0.74 to form a stable compound. But since there is a very large size of anion compared to cation, the packing efficiency of C3s, C2s, and C3a, they are not in this range. So to achieve this required packing efficiency, these unstable compounds, they incorporate water, which is what we call as water of crystallization within their structure to fill up the spaces and increase their packing efficiency to this range. And that is why cement reacts with water and form compounds which are known as hydration products. Okay, any doubt in the discussion till now? Any doubt in the basic understanding of different why different compounds are formed and why cement is reactive? Okay, so no, if there are no doubts, I will move ahead. Now, after knowing why cement is reactive, let's see how cement reacts with water. Okay, so first let's see what is the hydration of silicates. Hydration of silicates. So silicates, we have C3s and C2s, which upon hydration produces CSH gel and CH, calcium hydroxide. How it produces? So 2 moles of C3s, it reacts with 6 moles of H2O to form C3s and 3 moles of calcium hydroxide, which is also known as Portlandite. Okay, so if we are taking 100 grams of C3S, it will react with 24 gram of water to form 75 grams of CSH and 49 grams of CH. Whereas belite C2S, 2 moles of C2S, it reacts with 4 moles of water to form CSH and 1 mole of CH. So 100 grams of C2S, it reacts with 21 grams of water to form 99 grams of CSH and produce 22 grams of CH. Now, what is this CSH? So, CHS is the main strength pairing compound of cement. Okay, or in turn for concrete. Okay, and why we are representing CSH by this dash? Because it doesn't have a well defined composition. So, the C by S ratio, the CaO by SiO2 ratio in cement, it can vary from 1.5 to 2. Okay, so since it doesn't have any definite structure, we represent it with a dash. Okay, and the CSH is a poorly crystalline material and forms a porous solid which exhibits a gel-like nature, and that's why it is called CSH gel. Okay, and CH, it is also known as Portlandite, which precipitates out of pore in the pore spaces of concrete and is like prone to external exposure. Okay, so this was about hydration of silicates. Now, in case of hydration of aluminates, the reaction of alumina with water is very volatile and it leads to immediate stiffening of cement paste, which is known as flash set. So we already earlier a few slides ago we discovered that C3 is very reactive because of its simple open cubic structure. So when we add water to cement, the C3a phase in the cement, it reacts readily with water and it stiffens the paste, and this stiffening of paste due to addition of water is what is known as flash setting. Okay, so when cement water is added in cement, where is my cursor? Okay, when water is added in cement, so C3 it consumes 6 moles of water to form C3H6. This is known as hydrogarnet. Okay, so if we see in terms of weight, so 100 grams of C3 it reacts with 40 grams of water to form 140 grams of hydrogarnet, which is the responsible for flesh set in cement. Now, presence of C3A in cement, we know that's why presence of C3A in cement is undesirable, because it is contributing nothing to the strength of the cement. It is not forming CSH, which is the main strength bearing compound in our cement. It is not forming CSH, so it is not contributing anything to the strength of the cement, and it is causing premature stiffening of cement waste, which makes the system less workable. And in hardened concrete, it is susceptible to degradation due to sulfate attack. This we'll see later on. I have just mentioned the point here. So to encounter this problem with C3A, we add and eliminate the problem of flash setting, we add gypsum during the cement production. Okay. Now, though C3 is a problem to cement, it is still important. Why? Because it acts as a flux and it reduces the temperature of burning of clinker, and thus it facilitates the formation of combination of lime and silica. So in the clinker formation process, in the kiln phase, C3A act as a flux and it supports the reaction of the combination of lime and silica, which is very important to us to form clinker. That's why C3 is important. And then another positive side of C3 is that it binds chloride. So later on, when we'll talk about durability, we'll see that this is also a very important property which makes C3 a important compound. Now, we right now told to eliminate flash setting problem and to make cement pumpable or workable in practical application, gypsum is added at the end of clinker production. So what gypsum does? So gypsum, when added to cement, it controls the hydration rate of C3A. So it slows down the reaction of C3A with water. So when gypsum is present, what happens? C3A, it reacts with C3 and water to form what is known as ettringite, which is a more stable and slower forming compound compared to hydrocarbonate. Okay, so C3A in the presence of gypsum reacts with 26 moles of water to form ettringite. Okay, this reaction delays the stiffening process, it prevents the flash setting, and it allows cement to remain workable for a longer time. So that is why we add gypsum in cement. Now, as hydration continues, gypsum will be consumed by the C3A, and once gypsum is depleted, and if we have excess of C3A still in our cement, what will happen? This ettringite, it will react with C3A to form what is known as monosulfates. Okay, now this conversion of ettringite to monosulfate involves reduction in volume, which sometimes can lead to minor shrinkage in cement. And in hardened concrete, the presence of monosulfate is a problem. Why? Because it can react with the sulfates that are coming from outside and convert back into ettringite. Now, just before this line, we discovered that ettringite to monosulfate conversion reduces the volume. So, reverse will increase the volume. So, if monosulfate will convert into ettringite, there will be an increase in volume. But in a hardened concrete system, there is no free space for expansion. So, if such expansion occurs in a hardened concrete system, it can cause volume damage to the concrete, and that's why we say too much of C3 is also not desirable in cement. Okay, and sulfate attack is a problem to cement because of this monosulfate to ettringite conversion in the hardened system. Okay, any doubt in this part? Rehydration of aluminates and silicates. If anyone has any doubt, they can post in the chat box. And for others who don't have any doubt, just try to answer these two questions. What is the difference between flash set and false set? False set you may have heard during the live session, during the week one presentation audio lectures, and flash set we have just studied. And second question, from a durability point of view, which clinker phase is more important, C3A or C2S? Try to answer these two questions. Can you also tell why C2S? Flash that we have just studied, it is stiffening of cement paste in very early hydration age. What is the difference between flash set and fall set? What is fall set? Not so. It is false set. C2S due to low heat of hydration. It is incorrect. It produces low heat of hydration, but that is not the reason for its durability application. We'll see. Okay, let's see the answer for both. I'm guessing there is confusion in these two questions. So first, it is flash set. So as we just now discovered why flash set occurs, because C3A reacts with water to form calcium alumina hydrate, basically hydrocarbonate, okay, which causes immediate stiffening of cement paste. Okay, and we discovered 100 gram of C3A, it reacts with 40 grams of water to form CSH, and this we can see this 40 grams of water which C3A is consuming, it is way higher than what 100 gram of C2S or C3S would have required. Okay, so earlier when we saw the reactions of C2S and C3S, we saw how much water they consume. So C3S, it requires only 24 grams of water, while C2S requires only 21 grams of water for complete hydration. While C3A, it is requiring 40 grams of water. It is consuming much more water compared to other phases. Okay, so this is flash set due to immediate reaction, stiffening of cement paste. Now, false set is something different. Okay, if anyone has any doubt, they just post the queries in the chat box. Okay, so false set occurs when hemihydrite, hemihydrate, that is CaSO4 dot half H2O. When hemihydrate converts into, it combines with water to form gypsum. This is known as falset. Okay, so gypsum is basically CaSO4 dot 2H2. So this reaction is what is known as falset. Okay, now you all will wonder from where this hemihydrate come. Okay, so this can come, and this reaction, it is also known as plaster set. Okay, so when we talk about plaster of Paris that we use, it is the same thing. Hemihydrate, it consumes water to form gypsum. Okay, and this again, since it is consuming water, it can show stiffening in cement paste. However, unlike flash set, which is irreversible, this false set is a reversible process. So if we mix the cement again without addition of water, we can revert this reaction back. Okay, so false set is irreversible, whereas flash set is irreversible. Now, how this hemihydrate came into cement? So it can be present in cement if during the clinker production, if the clinker is too hot and we add gypsum to it. Okay, so if in too hot clinker we add gypsum, so gypsum can lose its water of crystallization and form hemihydrate, okay, which can lead to problems like false setting. Okay, so this is known as false set. So if we add gypsum in too hot clinker, it can form hemihydrate, which when we add water to cement can form gypsum and show false setting problem. Okay, so this is false set and this was flash set. So flash set is a irreversible process, whereas false set is a reversible process. Now between C3S and C2S, which is more important from a durability point of view, it is C2S. Why? Because it is producing less amount of CH. Okay, this is the reason. And it is producing more amount of CSH upon hydration. Okay, so CSH is the main strength bearing phase of cement, and CH is something which is undesirable to cement. So later on, when we'll talk about durability of concrete, you will see we don't want CH in concrete. CH is the reason why concrete faces durability issues. Okay, so compared to C3S, C2S produces less amount of CH. So that's why it is more important from a durability point of view. Okay, hemihydrate means CaSO4 dot half H2. So this compound is known as hemihydrate. And it can form if we had gypsum in very hot clinker. So gypsum will lose some water of crystallization and it will convert to hemihydrate. So to this cement, if we add water, the hemihydrate will first convert into gypsum, which will appear as a false set, and we can mistaken it with flash set. Clear? Okay, let's move ahead. Now we have talked about cement hydration. Okay, so let's see a flowchart how this hydration actually happen at a higher scale. Okay, so we have talked about from the microstructure point of view. Let's talk about the surface point of view how the hydration is happening. So one thing that you should remember is that cement hydration is a surface phenomena. So suppose this is a cement grain and we have water outside, so cement hydration is a surface phenomena. So from the surface, the hydration will start. Okay. So if I can draw it properly. Okay. So it is a surface phenomena. So this is my cement grain, and on the surface, my hydration reaction will start. Okay, so as written here, cement when it comes in contact with water, the hydration reaction takes place at the surface of the cement grain, and the reaction products are is formed at the surface. Now, the hydration product formed is gelatinous in nature. So we have already seen that CSH has a gel-like nature. It is poorly crystalline and it doesn't have any definite structure. That's why it is represented by a dash. So it has a gel-like nature. So this gelatinous product that is formed, it forms a coating over the surface of a cement grain, and this coating act as a semi-permeable membrane for water. So I have this cement grain. Okay, over the cement grain, I have a gel-like coating which is formed. Okay, and now this coating will act as a membrane for water to interact with the unhydrated cement. Okay, now due to this coating which is formed, the concentration of solute is higher inside the grain compared to this concentration of solute outside the grain. And due to this difference in concentration, there is osmotic pressure which increases. Now, when this osmotic pressure rises to a very high level, it breaks down the membrane which is formed, and water meets the unhydrated product portion of the grain, causing hydration to progress in both inward and outward direction into the voids between the grain. So what happens? We have this grain, okay, and we had this layer over the grain, okay. Now, as the layer, this gelatinous layer will grow, I will have unhydrated cement inside, Okay, and I have water outside. Now inside there is a lot higher concentration of solute, outside there is very low concentration of solute. So what will happen, there will be a osmotic pressure that will rise. Now as this osmotic pressure rises to a very high level such that it can break through this semi permeable membrane, when it reaches that level it will break the membrane and it will enter the this water will enter through the cement grain and it will react with the inner product. So that is how hydration proceeds. It proceeds from outside to inside slowly. Okay, now when the hydration products between each grain merge, it causes setting, okay, due to lack of water. And as the system becomes closely packed, it causes hardening. Okay, so when these two grains, when hydration products between these two grains they merge, it causes setting. And when this happens over the entire concrete composition and concrete starts to become stiff and closely packed, it causes hardening of concrete. Okay, so this is like from a surface point of view how cement hydration is occurring. So from the microstructure point of view, understood how cement hydration occurs, how reaction between different chemical compounds in water occurs. And in this slide, we understood how this reaction is actually happening. It is happening on the surface. Then there's deposition of hydration products on the cement grain, due to which there's rise in osmotic pressure. Once osmotic pressure rises to a very high level, it ruptures the earlier formed membrane, and this is how we see setting and hardening occurring in a concrete or a cement paste. Now, among different hydration products that we have talked about, let's talk about CSH. So, CSH is the main hydration product which gives strength to the cement paste assembly and subsequently to the concrete. So the exact structure of CHS is very complicated. Okay, it exhibits variable composition due to varying C by S ratio between the range of 1.5 to 2, and that's why it is written as C dot dash S dash H. Okay, surface area of CSH is also very high compared to Portland cement, which has a surface area in this range. That's why we see this is a cement grain. However, upon hydration, its size will look like this, and the unhydrated portion will look like this in the middle. Okay, due to very high surface area of CSH. The structure of CSH can be compared to the crystalline structure of tobermonite mineral. Okay, so like tobermonite, CSH also has a layered geometry. Okay, it has a calcium silicate sheets which are separated by interlayer spaces. So here you can see these are calcium silicate sheets. Okay, and there are spaces between the sheets. So this is the resemblance of CSH structure to what is known as what we see in a tobermonite mineral. Okay. And in CSH, there are two types of molecular forces which are present. There are covalent bond between silicate chain and the calcium ions, okay, and oxygen atoms, which provides a primary framework to the CSH, which is also known as the backbone of CSH. And there is in between the sheets of CSH, there is weak van der Waals forces which are present, which holds these sheets together. Okay, and that it enables like a chain interaction with the in the silicates, which is responsible for its gel like nature. So in CSH we can see there are two types of forces. These are sheets in within which there is covalent bond, and in between sheets we have van der Waals bonds. Okay, so at a very nano level we can see this is how different grains of CSH are arranged. Okay, so if we see from a higher micron level, we can see these green, they arrange themselves to form a granular structure. So we say CSH has a granular structure. Okay, and in cement paste, it appears like finely divided granules. These are CH, which has plate structure, and these are CHH in the bottom, which has granular structure. And at concrete and mortar level, it appears as a very fine granular particle near cement and aggregate junction, or what we call as ITZ. Okay, So this is the structure of CSH. Now, assuming that you all know the structure of CSH, CH, and maybe if you know other other compound structure also, just try and identify different hydration product in this image. Okay, so this is an image of cement hydration, and this image has different types of hydration products. Okay, so just try to identify based on location like bottom left, bottom right, top left, top right, middle. What type of hydration product can you see in this image? CSH you should easily recognize. Just now we have discussed. CH also you should recognize because I have just told you in the previous slide how CH appears. Try to also locate ettringite, monosulfate, and other things that you can see. My presentation should be visible. Uh, is the problem encountered by everyone? Am I audible? So, everyone are able to see my presentation, right? Okay. Try to answer this question. Identify different hydration products in this image. I will zoom this image so that everyone can see clearly. Just tell me based on location like bottom right, bottom left, middle, top right, top left, what they are able to see. What you are able to see. So needle-like portion are called ettringite. Yes, you are right. Where you can see these needle-like portion, middle of the portions are okay. Bottom center, okay. So let's see the answer for this question so that we can quickly move ahead. Okay, so in the bottom left here, we can see the granular structure of CSH and we can see attringite needles. Okay, these needle like structure that has been pointed by one of the student. So these are attringite and this is CSH. Okay, in the upper left side, you can see some plate like structure. Okay, some plates. Okay, these are monosulfates, which are also represented as AFM. Okay, in the right side, in the upper right side, you can see these crystal plates. Okay, these plates are of CH. Okay, so we have seen ettringite, we have seen monosulfate, we have seen CSH, and we have seen CH in this image. Okay, so this is also CH, this is ettringite again. These are calcium hydroxide, portlandite. Here you can see monosulfates. So this is how we identify different hydration products using scanning electron microscopy in a cement paste. Okay. Now we know how why cement is reactive, how cement reacts with water. So now let's talk about kinetics of cement hydration. So by the term kinetic, we mean the rate at which hydration occurs. Okay, so kinetic defines the rate of hydration. Okay, so basically, when we talk about hydration of cement, based on kinetic, it is divided into four stages. Okay, so we have pre-induction period, which lies in very first few minutes. So in this pre-induction period, there is rapid dissolution of ionic species, alkali ions, potassium ions, sodium ions, and sulfate ions. So they dissolve. Okay, we have C3 which dissolve and reacts with gypsum to form ettringite. We have C4AF which reacts with again gypsum to form ettringite. And we have CSH which starts forming on the surface of C3S grade. Okay, and very small portions of C2S react in this phase. Okay, so this is known as pre-induction period. Second, we have dormant period, okay, which lies for first few hours. Now, due to early hydration reaction, it appears to slow down in the dormant period. Why? Due to deposition of gelatinous layer of CSH on the cement grain that we discussed few slides ago. Due to this deposition of gelatinous layer, there is a membrane which is formed on the cement grain and which creates osmotic pressure, and only when osmotic pressure becomes very high enough to break the membrane, then only cement hydration proceeds further, and this period is known as dormant period. Okay, after dormant period, we have acceleration stage where nucleation and growth of CSH and CH occurs. So now my gelatinous layer is broken down. My osmotic pressure has reached to a higher value such that water is able to penetrate in. And now I have continuous hydration of my cement grain, and I am able to see CSH and CH formation occurring. Now, up till now, C3S was forming, C3S was reacting. Now, C2S also starts reacting. Okay, so C2S is generally a slow reacting compound compared to C3S. That's why we say lime is weaker in strength compared to cement, because in cement we have C3S also, which reacts readily compared to C2S, which is there in lime. Okay, this is also one of the reasons. Okay. In the post acceleration period, what happens? The rate of reaction again slow down due to decline in the non-reacted material. So my unhydrated cement grain will continue to decrease as the hydration proceed, and that's why my reaction rate will also slow down. Now in this period, major contribution comes from C2S as it converts into CSH, and my AFT phase starts converting into monosulfate if my sulfate contents have decreased and I still have AFM, and if I still have C3A in my system. Okay, so this conversion also happens in the post acceleration period. Okay. So in this slide, we can visualize different hydration stages. So in the first figure, you can see it represents progress of hydration versus hydration time. We can see that in the initial few hours, there is only C3 and C4AF that is reacting. And this period is known as dormant period. Okay. Then we can see in the acceleration stage, just a second. In the acceleration stage, C3S has also started reacting, and then in the post acceleration stage, we can see how C2S has also started reacting. Okay, so this is how a cement hydration progresses with hydration time. And in the second figure, you can see the finally formed hydration product, they how the formation of hydrate product changes with hydration time. So in the initial dormant period, we can see there is nothing much that we can see that has formed. Okay. Uh, in the setting period, that is the second stage, we can see, or we can say it as the acceleration period also. So in the setting or the acceleration period, we can see there is AFT and CSH formation start happening. CSH from C3S and AFT due to C3A and gypsum. Okay. And in the third stage, which is known as hardening stage, or we can say post acceleration stage, we can see CHS formation continues to grow because now contribution is coming from both C2S and C3S. We can see CH is also forming due to this hydration of C2S and C3S. And we can see here decline of AFT starts happening because AFT starts converting into AFM. Ettringite starts converting into monosulfate because there is still some C3A left and there is no sulfate there anymore. So C3A reacts with AFT to form monosulfate phase. Okay, so this is how we can visualize the compound composition and the hydration product composition over a hydration period. Now, just quickly answer the simple question. What is the order of reactivity of clinker phases? C2S, C3S, C3, and C4AF. Just now we have seen. Can anyone answer this? Heat of hydration, we'll see just like in 10 minutes what does heat of hydration means. Sir, Bogues compounds means Bogues is a just Bogues is a scientist who gave a equation to relate oxide composition to compound chemical compounds. There is nothing such as Bogues compound. It is just if we know the oxide composition, he gave a relation of how cement upon hydration converts into how different clinkers they bind to form a certain compound. So based on the oxide composition, what can be the compound composition? That relation was given by books. First, tell me the answer of this question. First, C2S, C3S, C4, C3A, and C4AF. Okay. Any other answer? Okay. So this is the correct answer. So the order of reactivity is C3A. We all know it is very reactive due to its open crystal structure. After C3A, we have C3S, which we also saw like in the initial induction period, we saw there is some formation of CSH. That formation of CSH is due to C3S. Then we have C4AF, which is reactive, and finally we have C2S. So C2S is the least reactive, and that's why it contributes to the late strength gain compared to C3S. Okay, so this is the order of reactivity. Uh, okay, let's move ahead. Now we shall talk about two important properties of cement hydration kinetics. These properties are heat of hydration and degree of hydration. Now, why these two properties are important? Because uh, they are basically the things which matters to us from application point of view, and these terms help us to choose various types of cement for our specific application. So later on in the week 2 content, we'll see different types of cement and special cements, and then we'll talk about heat of hydration and degree of hydration, why it is important. Sometimes we need a cement which is rapid hardening cement, we sometimes we need a cement which has low heat of hydration, sometimes we need a cement which should be slowly reactive. So all those things depends upon the heat of hydration of cement. Heat of hydration is a term that helps us to understand whether cement is highly reactive or slow reactive, whether it will produce more heat or less heat, and this things becomes important from application point of view. Okay, so first we have heat of hydration. So cement hydration we know is a exothermic reaction. It releases heat. Okay, so when cement reacts with water, it liberates heat. Okay, now the amount of heat released by clinker phase upon reacting with water is what is known as heat of hydration. So when a cement grain is reacting with water to form certain hydration product, it releases heat, and this heat released by this reaction is known as heat of hydration. So heat released due to hydration reaction. Now higher is the heat of reaction, higher is the heat of hydration, quicker is the reaction. Okay, so more the reaction will occur, more will be the heat of hydration. Okay, this is very simple. Now, different clinker phase have different heat of iteration. So C3S, it releases 502 joules of heat per gram. C2S releases 260 joules per gram. C3A releases 867 joules of heat per gram, and C4AF releases 419 joules of heat per gram. So this is in the same order like we saw in the previous slides, the order of reactivity. So higher is the reactivity, more is the heat of iteration. Okay, so C3A has the maximum heat of iteration, then we have C3S, then we have C4AF, and finally we have C2S. Okay, so in this figure, we can see different stages of cement hydration and subsequent heat evolution. So on the y-axis, we have just a minute. So on the y-axis, we have heat evolution, and on the x-axis, we have time. So initially in stage one, that is pre-induction period, we see a heat burst that is happening due to ionic movement. As ionic movements happen vigorously, and if there is no gypsum, there will be flash setting, which may also release a lot of heat. Okay, then once the initial kinetics had settled down and there is a CHH cover over the cement grain, the osmotic pressure plays a dominant role. We are in the dormant period, and thus we have a very low heat of iteration because reaction kinetics has slowed down. Once the osmotic pressure rises above the value, it breaks the semi-permeable membrane. Cement hydration again starts happening, which is what we known as acceleration period, and we again see a shoot in the heat of hydration. And as the cement grain starts to hydrate, my unhydrated cement proportion will decrease, and so my heat of hydration will also slowly decrease. I will reach stage 4. Okay, and then this is post acceleration period. Okay, stage 4, and then I will have stage 5, where hydration has significantly slowed down, and we have a very steady decrease in heat of hydration, or very steady, very stable increase in total heat of hydration. Okay, so if we want to estimate heat of hydration, how we can estimate? So we can just sum the heat of hydration of individual compounds. So suppose we have C3S, we know how much joules of heat it will regulate per gram. We have C2S, we know the value of this. For C3A, we know the value of heat of hydration. And for C4AF, we know the value of heat of hydration. So suppose I have 100 grams of cement and I know the chemical proportion, compound proportion of the cement. So I know it has 60 grams C3S, 20 grams C2S, 10 grams C3A, 10 grams C4AF. So I can just take 60 grams CSH multiplied by its heat of hydration, 20 grams of this multiplied by its heat of hydration, 10 gram of this multiplied by its heat of hydration, and 10 grams of this multiplied by its heat of hydration. In this way, we can calculate the total heat of hydration. After heat of hydration, we have degree of hydration. So basically, as we saw earlier, it is a measure of how much water has reacted with cement. So earlier we also saw in one diagram here, progress of hydration and hydration formation. It is how much water has reacted with cement, and this is known as degree of hydration. Okay, now we know cement hydration is a long process. It continues over a long period. That's what we can see in the first figure. So how hydration after initial steep increase, it continues to increase in a very steady pace till 28 days. Okay, so here you can see after initial steep increase, my degree of hydration increase has become very steady and stable up till 28 days. Generally, after 28 days of addition of water to cement, we say that more than 99% of hydration is completely completed. However, this statement will not be true in case of mineral admixture. We'll see later on why. And this is how a degree of hydration progresses with age. In the second image, in the second figure, you can see the volume fraction of unhydrated and hydrated cement, how they are changing at different times. So this is 0 R, this is 0.4 R, and this is 0.8 R. So initially, When we just add water to cement, we have unhydrated cement and we have capillary water. After zero point 0.4 hour, we can see there is gel solid and gel water. These are resulting from hydration product formation, which has showed up, and this increases further at zero point 0.8 hour. We have more amount of gel solids and gel water, and subsequently we can see that the unhydrated cement and the capillary water proportion is decreasing. So this progress of consumption of water as by cement is known as degree of hydration. Now just quickly estimate what is the heat liberated by the cement composition, so that you just have a practice of the formula. Just do the calculation quickly. So if anyone has done the calculation, the answer will be 466.56 joules. So this is the heat of iteration of this cement composition upon reaction with water. Okay, you can verify this value later on upon by yourself also. We'll move ahead for now. So now we have an idea of cement hydration and properties of cement hydration, but there are two more important entities that are associated with the hydration of cement. One is water and the other is porosity. So first, let's talk about different types of water in a cement hydration, in cement hydrate system. So we have three types of water when we talk about cement hydration. So we have capillary water, we have gel water, and we have chemically bound water. So capillary water refers to the free water that is present in the pores inside the cement phase, which upon evaporation won't cause any shrinkage. And these are the water which are held by capillary tension in small pore, which causes shrinkage strain upon drying. Okay, so capillary water is basically the unreacted water, we can say. Okay, so in a cement water system, some water will react and some water will still be there in the system, and that unreacted water is known as capillary water. So these are present in between pores of hydration product. Okay, they can evaporate easily and it won't cause any shrinkage strain. And if this water is held by some capillary tension in small pores, in large pores, if they evaporate, it won't cause any shrinkage strain. However, if from small pores it evaporates, it can cause some shrinkage strain upon drying. Then we have gel water. Gel water is the water which is held in between a hydration product. Okay, so gel water is of two types: adsorbed water, the water which is absorbed on the surface of hydration product, primary CSH, and interlayer water, the water which is held in between layers of CSH. Okay, so if gel water dries off, it can give rise to a lot of shrinkage and even collapse of CSH structure, and this requires higher temperature compared to the temperature that we require for release of capillary water. Okay, it will require higher temperature. And finally, we have chemically bound water. So this is the water which have actually participated in the hydration process. So when we write cement is hydrating with upon reaction with water, it forms CSH. So this H that we have written here, it is the chemically bound water. Okay, and this can only be removed upon ignition to very high temperature. Okay, the same we can see in this structure which was given by Friedman Sereda, which is known as Friedman Sereda model, okay, of CSS structure. So we can see here, this is the region of capillary water. Okay, in between hydration products of CSH. On the surface of CSH, okay, these are the two silicate sheets. Okay, and this is the space between the silicate sheet. So on the surface of the silicate sheet, we can see these are physically adsorbed water, which is gel water, and in between the silicate sheet, there is water which is held, which is known as interlayer water. And the water that is actually consumed in forming this sheet is known as chemically bound water. Okay. Now, if we specifically talk about chemically bound waters, it can be estimated by if we know the degree of hydration. So, suppose C3S, how much water it requires for complete hydration, C2S, how much water it requires for complete hydration, C3A, how much water it requires for complete hydration, and C4AF, how much water it requires for complete hydration. If we know all these values, we can estimate the chemically bound water. Okay, so here A1, A2, A3, A4 represents the amount of water that is consumed by different compound for complete hydration. So there are several studies which has estimated these value of A1, A2, A3, A4, and they have found that for C3A we require 0.23 fraction of water. For C2S we require, so for 1 gram of C3A we require 0.23 gram of water for complete hydration. For 1 gram of C2S we require 0.196 gram of water. For 1 gram of C3A we require 0.522 grams of water, and for 1 gram of C4AF we require 0.109 grams of water for complete hydration. So if you assume a OPC cement having composition like this, then we can estimate the chemically bound water upon complete hydration as 0.23 times 48 plus 0.196 times for 25 plus 0.522 times 11 plus 0.109 times 9. So this will come out to be 23 grams. So we can say 100 grams of OPC, it will require 23 grams of water for complete hydration. It is a very important line that one must remember. Okay, so if you want to completely hydrate a cement, OPC cement, we require at least 23 grams of water. Now, after water, we have porosity. Okay, so my cement when my cement is reacting with water, it is forming hydration product. There will be some spaces in between hydration products also, and these spaces are known as porosity. Okay, so porosity in cement paste can be broadly classified into three types based on its size. So we have gel pores, which are extremely small, which in the range of 1 to 10 nanometers, and they are found within the gel structure of hydrated cement, primarily in between the CHH layer. So CSH layers, in between these two CHH layer, the pores that are present are known as gel pores. When its size is very small, 1 to 10 nanometer. Okay, it influences shrinkage and creep properties like we discussed for water. Then we have capillary force. It has size in the range of 10 nanometer to few micrometer. And these are the water field spaces in the paste that has not been occupied by the hydration product. So the water that has not actually participated in the cement hydration, which is still there in the system, they form the capillary pores. And this water influences the strength and the durability property. This pores. Then we have macropores, which size is greater than few micrometers. So they result from incomplete compaction, large voids, or entrapped air during mixing or placing of concrete. So during concrete, if we don't do proper compaction, or there is some air which is entrapped in the molds, then the pores that we get are known as macropores, and which are very undesirable, and they can affect the integrity of a cement paste. Okay, so when we are talking about cement paste right now, for us there are two types of pores which are important. One is capillary pores and one is gel pore. Macro pores generally comes when during concreting if compaction is not done properly. So in this figure, we can see how these porosity lie on a dimensional term as compared to hydration product. So we have CSH, which has a size of very few nanometers. In between CSH, interparticle spaces between CSH, there is gel pore here. Okay, a capillary pores lies in this range. Okay, which is smaller than the aggregation of CSH and CH size. And then beyond 100 micrometer, we have entrapped air bubbles and entrapped air voids, which are not desirable for concrete. In the second figure, we can see a simple illustration of CSH hydration and where the porosity lies. So these are sheet structures of CSH, and this is capillary pores, which is like the unhydrated portion of my cement paste. And in between CSH layer, these are gel pores. Okay, these pores are generally filled with water, but if we remove the water from the system, it will appear as a air void. Okay. So let's finally see this question on estimating gel porosity and capillary porosity. I saw in the discussion forum that a lot of students generally encounter the problem in calculation of this gel porosity and capillary porosity. So we'll just discuss this question. So this question says estimate the gel porosity and capillary porosity of a cement paste assembly prepared by mixing 100 grams of cement with 35 grams of water, assuming 75% hydration is completed. And you can assume that the density of hydrated cement is 2.51. We can take to be accurate, and 28% of the volume of hydrated cement paste is consist of gel pores. Okay, so just give it a try. It is a like a little bit of lengthy calculation. I don't expect that everyone will be able to complete in a small time, but I will wait for a couple of minutes. Just give this question a try, and in the meantime, for those who don't know the calculation, they can wait and they can ask their queries in the discussion that we had till now. It's good that you are helping each other out. Okay, so I will mute myself for like a couple of minutes, and I will let you people just give this question a try, and then I will tell you the solution. Since we have very less time left, I will just start the solution. Everyone just see the steps that I am using properly, so carefully, so that you can also try it on your own later on. Okay, so first I have written all the things that I know. So I know the mass of cement, I know the density of cement. I have assumed it as 3.15. Generally this is the density of OPC cement. Okay, I have as mass of water I know, and the density of water I know. I know the degree of hydration, and I know the density of cement paste. So first part will be to calculate the volume of anhydrous cement paste. So what will be the volume of anhydrous cement paste? It will be the volume of cement, which is mass upon density, plus volume of water, which is again mass upon density. So we know density is equal to mass upon volume. So volume will be equal to mass upon density. So this is specific gravity we know, and from that we can calculate density. This is 1 gram per centimeter cube, and for relatively for everything. Okay, so this value will come out to be 66.74 cubic centimeter. Okay, now for 75% degree of hydration, the volume of hydrated cement will be, assuming that 23% water is required for complete hydration. This is what we have just derived in few slides ago. So assuming this statement is true and my degree of hydration is 75%, so my volume of hydration product will be 100 plus 23 times 100 into, this is my mass of cement. Okay, so this will be 1.23 times, sorry, not 100 plus 23. So 1.23 times mass of cement times degree of hydration, that is 0.75, divided by density of my hydrated product, which is 2.51. So this value will come out to be 36.75 cc. Okay, I will take a new slide. So this is my step 2 to calculate volume of hydrated cement. Okay. Now third step is to calculate volume of gel pores. Okay, so it is given that gel porosity, which I will represent by WP, WG I should write, okay, is 28% of total hydrated product that we have assumed, and we know this assumption. So what we can write, my gel porosity WG upon total volume of hydration product will, which will be 36.75 plus WG. Since gel porosity is also a part of my hydration product, so the total volume of hydration product will be actual hydration product plus gel porosity. So this value I know is, it is equal to 28% or 0.28. Now we know hydration product volume, that is 36.75. So upon rearranging, we will get WG equal to 14.29 cubic centimeter. So this is my gel porosity. Okay. Now step 4. What is my volume of unhydrated cement? Since there is only 75% hydration that has occurred, so my volume of unhydrated cement will be 100 times 1 minus 0.75 divided by 3.15, which will be equal to 7.94 cc. Okay, this is my volume of unhydrated cement. So I know the volume of unhydrated cement, I know the volume of hydrated cement, and I know the initial volume of my system. So knowing all these three things, I can calculate the volume of capillary porosity, which will be equal to total initial volume minus volume of unhydrated cement minus volume of hydrated cement. Okay, so my capillary porosity I can write like this. So it is basically what is the initial volume of my system. So it will be volume of cement plus volume of water. From that volume, there is hydration products which are formed, and there is some volume of unhydrated product which are still left in the system. Okay, so that will give me the volume of capillary porosity. I have volume of anhydrated cement and I have volume of leftover water also. So 23 grams of water was consumed and I had 35 grams of water. So what is the volume of water left? It is 12 cc. Okay, so volume of capillary porosity. This water will go in the capillary porosity itself, so we don't need this. Okay, it is a part of capillary porosity only. So it will come out to be 66.74 total anhydrous volume minus volume of anhydrous cement 7.49 minus volume of hydrated cement, which is 36.75, which is equal to 7.74 ml. Okay, this is my volume of capillary porosity. So this is how we calculate the volume of capillary porosity and volume of gel porosity. This value will come out to be 22.05 cc. Sorry. Everyone clear with this calculation? How to calculate capillary porosity and gel porosity? Okay. So this was all for today's session. So we first had an overview of infrastructure development in India. Then where we talked about concrete and different concrete types. We had basic overview of concrete as a construction material. We discussed about cement as a binder system, and we discussed in deep about cement, how it is produced, oxide and compound composition, structure, hydration, degree of hydration, and heat of hydration. And finally, we talked about water and pores present in the cement system. Thank you. So you can find the recording of this session on YouTube channel. So the link to the session will be shared to you by the NPTEL team. So if anyone has any doubt or if you have missed any portion due to voice breakage, you can check the YouTube channel.